Good morning. Today I am going to teach you some calculations. First, empirical formula. An empirical formula represents the simplest whole number ratio of various atoms present in a compound. Second, molecular formula. Molecular formula shows the exact number of different types of atoms present in a molecule of a compound. Let me illustrate this with the help of an example. Let us take the example of glucose. Molecular formula of glucose is C6H12O6. Thus, molecular formula shows the exact number of different type of atoms present in the molecule of the compound. The same glucose will have empirical formula C1H2O1. So, empirical formula represents the simplest whole number ratio of various atoms present in a compound. Let us solve a problem, and thus I will tell you how to calculate the empirical formula and molecular formula. So if you read this problem, a compound contains 4.07% of hydrogen, 24.27% of carbon and 71.65% of chlorine. If the molar mass is 98.96, what is the empirical and molecular formula? So these are the different steps for calculation first of the empirical formula. There are three elements: hydrogen, carbon and chlorine. And from the data given in the problem, the percentages are 4.07 for hydrogen, 24.27 for carbon and 71.65 for chlorine. In the next step, we have to write down the atomic mass of each of these elements. As you all know, hydrogen has atomic mass 1.008, carbon 12.01, chlorine 35.4. In the next step, you will be dividing each of the percentage by their respective atomic mass. As you see over here, 4.07 divided by 1.008, 24.27 divided by 12.01 and 71.65 divided by 35.5, and you will get the answers. Now, in the next step, you will divide each answer by the smallest answer. Here both these answers are same and they are smallest. So you can divide each of the answer by the smallest answer, as I have done over here. For hydrogen, 4.04 divided by 2.02, and carbon and chlorine, of course, 2.02 divided by 2.02. Finally, this result will be the empirical formula. For hydrogen, 2, for carbon 1 and for chlorine 1. So empirical formula will now be C1H2Cl1. Next, how to calculate the molecular formula. In the problem, molar mass is given as 98.96. We have found that empirical formula was C1H2Cl1. So we have to find out empirical formula mass, that is the mass of C1H2Cl1, like this. 12.01 is atomic mass of carbon, 1.008 atomic mass of hydrogen multiplied by 2 because you have two atoms over here, and 35.4 is the atomic mass of chlorine. Answer 49.48. Next step, you will divide the molar mass with the empirical formula mass. 98.96 divided by 49.48, which is approximately equal to 2. Thus, that answer 2 you multiplied with the empirical formula to get the molecular formula. 2 into CH2Cl will give you C2H4Cl2, which is the molecular formula. So from the definition, molecular formula shows the number of atoms exactly present in the given molecule of the compound, and empirical formula is the ratio of the number of atoms present in the given compound. My next topic is stoichiometry and stoichiometric calculation. What is the meaning of the word stoichiometry? The word stoichiometry is derived from two words, stoichio and metron, where stoichio means element and metron means calculation or measurement, which means we have to measure the amount of the reactant and the products involved in a chemical equation. This is an example of a balanced chemical equation. From this balanced chemical equation, we can gather certain information. Here CH4, 1 CH4 combines with 2 times O2 giving 1 CO2 plus 2 times H2O. These are the reactants and these are the products, that is methane and dioxygen are the reactants and carbon dioxide and water are the products. 1 and 2 are the coefficient of the reactant methane and dioxygen. Here 1 and 2 are coefficient of the product carbon dioxide and water. Let us see what this 1 and 2 represent or what information we get from these coefficients. First, 1 mole of methane reacts with 2 mole of dioxygen to give you 1 mole of carbon dioxide and 2 moles of water, or 1 molecule of methane reacts with 2 molecules of dioxygen to give 1 molecule of carbon dioxide and 2 molecules of water. Now, 1 mole is equal to the molar mass. So, 1 mole of methane means 16 gram. I have got 16 by calculating the molar mass of methane, 12 for carbon and 1 for hydrogen. So, 12 plus 4, 16. 16 grams of methane. Similarly, 16 of 1 oxygen. So, O2, 32. So, 2 into 32 which is equal to 64 gram. 2 moles of dioxygen is equal to 64 gram. 1 mole of carbon dioxide is equal to 44 grams of carbon dioxide, and similarly 2 moles of water will be equal to 2 into 18 which is equal to 36. Once again 44 comes from 12 of carbon, 16 of 1 oxygen. So 16 plus 16, 32 plus 12 will give you 44, and water 2 of hydrogen and 16 of oxygen. So 18. 2 into 18 will be equal to 36 grams. Moreover, since the reactant and the products over here all are gases, we have one more information that 1 mole of methane is equal to 22.7 liters of methane. 2 mole of dioxygen will be equal to 2 into 22.7 liters of dioxygen. Similarly, 1 mole of carbon dioxide is 22.7 liters of carbon dioxide, and 2 moles of water vapor will be 2 into 22.7 liters of water vapor. Let me show you a problem of stoichiometry using the same equation. The problem is, how many moles of methane are required to produce 22 grams of carbon dioxide after combustion? So, from the balanced chemical equation, you know that 1 mole of methane will produce 1 mole of carbon dioxide. That is, 16 gram of methane will produce 44 gram of carbon dioxide. In your problem, they have asked you how many grams of methane you need to produce 22 grams of carbon dioxide. Since half of 44 is 22, half of 16 over here will now be 8. So 8 grams of methane is required to produce 22 grams of carbon dioxide. If 44 grams is equal to 1 mole, then 22 gram will be half mole. And from stoichiometry, you know that 1 mole of carbon dioxide is produced when 1 mole of methane is burned. So to produce half mole of carbon dioxide, you will need half mole of methane. The answer is half or 0.5 mole.